Okay, so today we're going to be talking about partial pressures of gases. So far in our gases chapter, we have been talking about the ideal gas law of PV is equal to nRT, where N here stood for moles of gas. Now that is very vague. It could mean that you have all one gas, or that you have a mixture of gases. So both of these containers, if we look real closely, they are the same size box and there's the same number of gas molecules inside of each. So both of these boxes contain the same number of moles of gas. And so if these boxes are at the same temperature, then since they have, so if they're at the same temperature, since they have the same number of moles of gas and they have the same volume, they will have the same pressure. But when we talk about partial pressures of gases, we're really interested in this mixture side of things. And what is the pressure due to each component? How much of the total pressure is due to the blue molecules, and how much of the total pressure is due to the green molecules? And so we can split apart that total pressure into separate partial pressures. So Dalton's law of partial pressures says that the total pressure will be equal to the sum of the partial pressures of each component. And so the number of moles of gas A will be responsible for the partial pressure of this first box, and then the partial pressure of the second box would be due to the number of moles of gas of the other green box, green molecules. So let's see if you understand this concept by doing a practice problem. The contents of two 5-liter containers, one containing hydrogen gas and the other containing helium gas, are combined as depicted to the right. And so this is the combined one. What is the final pressure of the 5-liter vessel? So all of these are 5-liter vessels at 20 degrees Celsius. How about you go ahead and pause the video until you figure out what you think the total pressure is in that container. Okay, now that you've unpaused the video and you have an answer, let's figure out what it is. So our total pressure will be equal to our pressure due to hydrogen gas plus our pressure due to helium gas. And so our total pressure is equal to 2.4 atmospheres plus 6.0 atmospheres for a grand total of 8.4 atmospheres. Another way of solving the problem is by looking at the total number of moles. And so we could add up those moles in order to get the total number of moles. And so that's 0.5 plus 1.25 moles, which is 1.75 moles. And then we can apply the ideal gas law. So if we have PV is equal to nRT, I could make that N total, and that would give me the total pressure. And so I know volume, I know temperature, and so I could solve the problem that way as well. But the correct answer is D, 8.4 atmospheres. Come on, move to the next slide. Okay, so we have some different ways of solving these partial pressure problems. One way of solving these partial pressures problems is to find the mole fraction. And so the mole fraction is often given a symbol of kind of a cursive slanted X. And then you would label it with what substance you are looking at the mole fraction of. So if you want to know the partial pressure of component A, then the partial pressure of component A will be equal to the moles of A divided by the total number of moles times your total pressure. So partial pressure is equal to P total times NA divided by N total. And so this is what we call the mole fraction. And so that mole fraction, it's kind of like when we did our mass percent composition, where we're looking at the number of moles of one component out of the total number of moles. And so when we did mass percent composition, it was mass of one component and total mass. And so this is kind of similar, only we're not going to be turning it into a percentage. A different way of solving partial pressure problems is to look at the ideal gas law. And so we know the ideal gas law says that PV is equal to nRT. Now that doesn't specify whether that's total pressure or if that's the total number of moles. And so we could just look at one component. And so if we want to know the partial pressure of component A, then we can just focus in on the moles of component A. And similarly, if we want to know the total pressure, then we can use the ideal gas law, only now we would use the total number of moles. All right, so here's an example problem, and it says, what is the partial pressure in atmospheres of N2 gas in air? So if we look at this table over here, we have our total pressure here, and we are given a percentage. So as I said before, this percent here is pretty similar to our mole fraction, only that's a percentage and the mole fraction is not a percentage. And so my mole fraction of N2 will be equal to the 78.2 converted back into a decimal. And so I can do that by dividing by 100. That's going to move the decimal place over twice, so that I end up with 0.782. So then that's my mole fraction. Mole fraction doesn't have any units because moles divided by moles cancels out. And so then my partial pressure of N2 will be equal to my total pressure, which is this number down here, 760 millimeters of mercury. And it's asking for my pressure in atmosphere. So I'm going to go ahead and lay out a conversion between millimeters of mercury and atmospheres, because that's what the question is asking for. So 1 atmosphere is 760 millimeters of mercury. That is from your yellow sheet. And next I'm going to multiply by my mole fraction. And so that's 782. 78.2. Wait, 72. All right, where did I put my calculator? Ah, I see it. All right, so if we do that, then that's 760 divided by 760 times 0.782. And then my final unit will be atmospheres. You could have also just looked at the table here and that is 594 millimeters of mercury. And so another way you could solve this, or at least figure out how they came up with that 594 number, is that 594 millimeters of mercury is the partial pressure of N2 in a different unit. And then we just have to convert it into our partial pressure. So that's just converting it into atmospheres. But you can see that we'll get the same answer as we did above using our mole fraction. So 594 divided by 760 is 0.78157 atmospheres. And then 3 sig figs is 0.782 atmospheres. So we got the same answer that they had in the table. Okay, so here's another practice problem for you. It says a sample of air contains this many moles of N2, this many moles of O2, and this many moles of argon, and this many moles of CO2. What is the partial pressure in bars of O2 at 25 degrees Celsius if the above mixture is in a 20.0 liter container? And so we want the partial pressure in bars. Go ahead and pause the video and see if you can work out what the partial pressure in bars is. Okay, so let's see if you got the same answer that I'm going to get, or if you did it in the same way. So since this is asking for the partial pressures in bars, I'm going to look up here to my different units for R, and I see that this R value has bars listed. So I'm going to choose that R value to make my unit life easy. Next, I know that PV is equal to nRT. And so since I'm looking for the partial pressure of O2, I can just focus in on O2, and that would give me the partial pressure of O2. So I have to isolate P on one side of the equation by dividing both sides by V. The V's cancel out, and so that simplifies to P is equal to, well, that's my partial pressure of O2 is equal to my moles of O2 times RT divided by V. So when I'm plugging numbers into the equation, I have to make sure that I'm matching my units of R, and we can do that quick analysis before we get too carried away. So my R says that my volume should be in liters, which it is, and my temperature needs to be in Kelvin. So I need to convert this temperature to Kelvin. So when I convert that to Kelvin, I have to add 273.15. That is on your yellow sheet. And so grabbing my calculator, that is 25.0 plus 273.15. And so that is 298.15 Kelvin. And so that is significant to the 10th place, and so this is significant to the 10th place from our addition rule. Now that everything is in the right unit, I can come back around and I can say that my pressure due to O2 is equal to my moles of O2, which is 2.095 moles. And then I can multiply by my R, which is 0.08314 liter bar per mole Kelvin. And then I can multiply by my Kelvin temperature, which is 298.15 Kelvin. Then I can divide that by my volume, which is 20.0 liters. So 2.095 times 0.08314 times 298.15 divided by 20. And so that is 2.59656 ... And then my final unit, that mole cancels with that moles, that liters cancels with that liters, this Kelvin cancels with that Kelvin, and I'm left with bars. And so as far as sig figs go, this volume has 3 significant figures, and that's the least number of sig figs. And so I'm going to round to 3 sig figs. And so that will be equal to 2.60 bars, which is option C. Now, there's a different way of solving this problem. So let's go ahead and erase all of this and solve it a different way. So another way you could solve the problem is using our partial pressures of O2. And so that says that my partial pressure of O2 will be equal to my total pressure times my mole fraction of O2. And so my mole fraction of O2 is equal to my moles of O2 divided by my total number of moles. And so that is equal to 2.095 moles divided by my total moles. To get my total moles, I add up all of these different mole amounts. And so we have to add that. And so we have 7.808 plus 2.095 plus 0.0934 times 0.00350. Let me make sure I typed that into my calculator right. I don't think I typed that in right. Yeah, there we go. So my N total is equal to 9.9999 mole. So my mole fraction is equal to 2.095 divided by 9.9999, which is equal to 0.2095. And again, there's no unit because the moles cancels out. Next up, we have to find P total because we don't know P total yet. So to find P total will be equal to my moles of total times my R times my temperature, and then divide that by V. That's the same type of using the ideal gas law to solve for pressure that we used this just before. So when I plug in numbers into that equation, I use my N total, which was 9.9999 moles. Multiply that by my R, which was 0.08314 liter bar per mole Kelvin. Then I need to multiply that by my Kelvin temperature, which, if I look back in my calculator, was 298.15 Kelvin. And then I divide that by the volume, which is 20.0 liters. And so typing that all into my calculator, I get 9.9999 times 0.08314 times 298.15 divided by 20. I end up with a number that is 12.3928. And then the final unit on that is bars. And so I'm still not done with the problem. That is my P total. And so based on my original equation, I have to take P total and multiply P total by my mole fraction. So I have to multiply those two numbers together. So my partial pressure of O2 is equal to 12.3928 bar times 0.2095. So grab my previous number, and then I end up with 2.596329 bar. And once again, this P total has 3 significant figures because of the volume, and so this number has 3 significant figures. And so once again, we end up with 2.60 bars. So both methods work, but you can tell that one method took a lot longer than the other method. And so once you get familiar with the concept of partial pressures, you'll be able to decide, based on the information I'm given, which problem-solving strategy should I employ. Sometimes you're given enough information to solve the problem in more than one way, and other times you're limited and you can only solve the problem in one way. And so, moving on. When we do our laboratory experiments, we often do chemical reactions that produce gas, and we can use the amount of gas that's formed in order to figure out how much we started with or something similar. And so this is an example of a chemical reaction that's producing gas. And so there's a metal that's reacting with hydrochloric acid, and we collect that hydrogen gas that comes off. So remember, hydrogen is one of our diatomic molecules. And so as this gas produces hydrogen gas, that hydrogen gas bubbles into this container and is collected over water. Now, whenever you have a liquid, you have some molecules of that liquid in the gas phase above the liquid. So if you have water in the liquid phase, then you're going to have some water molecules in the gas phase above that same liquid. That's because of the vapor pressure of water. And so we learned in chapter 7 about vapor pressure and how vapor pressure is related to like how much is in the gas phase, how much pressure from the vapor above the liquid is exerted back on the liquid. So this vapor pressure of water depends on temperature. And as we increase the temperature, we're going to get more and more of these water molecules in the gas phase. But the main point is that we have a mixture of gases inside this collection tube. We don't just have hydrogen like we're interested in. We have water vapor as well. And so when we do these lab experiments, we're going to have to subtract out the vapor pressure of water. So the vapor pressure of water we're going to look up in a book. Since the vapor pressure of water depends on temperature, we have to look that up. So we will reference that based on whatever temperature our reaction is in. This is what we're solving for. And these two, the pressure of the atmosphere and the pressure of the gas, will be equal once the two levels of liquid are the same on both the inside and the outside. And so this P total, we will look up. We won't look up, but that's measured from the external pressure. So that's the total atmospheric pressure. Hold on, I gotta silence my phone. Someone keeps texting me. Okay, so we will do an example problem of this. Okay, so here's a practice problem. It reads, the decomposition of potassium chlorate produces O2 gas and solid potassium chloride. If 124 milliliters of O2 is collected over water at 762 millimeters of mercury of atmospheric pressure at 20 degrees Celsius, how many moles of O2 are produced? So go ahead and pause the video and try to work this out on your own. All right, so now that you're playing the video again, hopefully you have an answer. And so let's go ahead and talk about this. This says that we are finding the number of moles. So let's always remember what we're trying to find. We are trying to find moles, which is abbreviated N, of O2. Now, let's look at the information we're given. We are given several pieces of information. We are given volume. Milliliters is a unit of volume. And my R values are always in liters. And so I'm going to convert that to liters. And so there are 1,000 milliliters in 1 liter. And so that is 0.124 milliliters. And then it's collected over water. And so that means that we're going to have to look up the vapor pressure of water. So we have to look up the vapor pressure of water. And so to figure out the vapor pressure of water, we have to look at the 20 degrees Celsius temperature, come over to our table. And so at 20 degrees Celsius, then our vapor pressure of water is 17.5 millimeters of mercury. Next, we are told that there is 762 millimeters of atmospheric pressure. So that's my P total. And so P total is equal to my pressure of O2 plus my vapor pressure of water, since this is collected over water. I'm interested in solving for my pressure of O2 because after I know my pressure of O2, I'll be able to plug into the ideal gas law and solve for the number of moles. So I am told that my total pressure is 762 millimeters of mercury, and that's equal to the partial pressure of oxygen plus my 17.5 millimeters of mercury. So in order to isolate the partial pressure of oxygen from both sides, I have to subtract 17.5 from both sides. And so my partial pressure of O2 is equal to 762 minus 17.5, which is 744.5 millimeters of mercury. Next, I'm going to convert that into atmospheres because I don't have my yellow sheet with me, and so I don't know the R value with millimeters of mercury off the top of my head. And so I'm going to convert that to atmospheres. so that I can plug this into the ideal gas law with an R value I know. If you have the yellow sheet, you can use the one that's in Tor, and then you won't have to do this. You can do it both ways to prove to yourself that you'll get the same answer in the end. I'm keeping extra sig figs. So that was in atmospheres. Let me track my sig figs though before I get lost. So when I do this subtraction earlier, then my P total was significant to the ones place, and so after subtraction, it's only significant to the ones place. And so now when I count sig figs for multiplication, I have 1, 2, 3 sig figs here. And so that means my pressure has 3 significant figures. So now I need to solve for my moles of O2. So PV is equal nRT. Isolate your N. Divide both sides by RT. And then we will end up with N is equal to PV over RT. And so N, in this case, is going to be O2. I'm going to use my pressure of O2, which was 0.979605. I didn't write the 5 earlier. Atmospheres times my R, no, times my V. My V was 20 liters? No, it wasn't 20 liters. It was 0.124 liters. And then I divide by my R, which is 0.082058 liter atmospheres per mole Kelvin. And then I multiply that by my Kelvin temperature, which is, oh, I haven't calculated that yet. So my temperature was 20 degrees Celsius, and so I add that to convert that into Kelvin. So convert that to Kelvin, and you get 293, that's 293.15. 293.15. And so then you have 0.979605 times 0.124 divided by 0.082058 times 293.15. And so that is 0.005049657. And then that's my moles of O2. And now I have to worry about sig figs. There are 3 significant figures in my pressure. There's 3 significant figures in my volume. And once I convert that into Kelvin, that's significant to the tenths place. And so there's actually 4 significant figures in my temperature. So now I'm around to 3 sig figs. And so that is 0.00505 moles of O2. So you can go through the typed math as well. All right, that concludes our talk about partial pressures.